Welcome to this last class, last topic of the fall semester. As you probably are aware by now, and you will not be surprised, this class is going to be focusing on a bunch of new technical words, and some of which you see right now. You probably heard these words, well, some of them at least, and probably you have some idea what they mean, but as usual our task will be to try to understand exactly what they mean and how they're used in statistics, so that when we see them in research papers, I can have a good understanding of what the authors were trying to talk about and how to use those in real situations. So just for a little recap, let me remind you that a probability is a number between 0 and 1, and it is a number that we use to measure the likelihood of an event to occur. As such, any unpredictable event can be studied for its probabilities. So what does that mean? Anytime that we're dealing with something that we're not sure if it's going to happen or not, then we can try and attach some probability to it to have an idea of how likely this thing is to exist. And because of this, of course, a lot of things that happen in your clinical nursing practice will have probabilities attached to them, from the probability of a patient being healed to the probability of having some kind of an accident during a day, to the probability that you will get a raise. I don't know. I mean, there's all kinds of things. The list never ends. However, what we're going to be looking at today are certain events that have a specifically clinical connection to probabilities. So in other words, there are certain events whose probabilities have a really important and a clear clinical meaning. And so they're going to be used on a fairly regular basis. So let's start from some probabilities that have to do with epidemiology. Remember, epidemiology, we're studying the spread of and the existence of diseases. So we're trying to figure out conditions and diseases and so on, how much they occur, where they occur, and so on and so on. So some of the basic ideas in epidemiology are the following. We'll talk about prevalence or prevalence rate of a condition. And now by condition here I mean something very vague, from a disease to basically something just happening. So try to keep it vague. We're going to see in class through some examples how this thing is applied. But again, just doesn't have to be necessarily a disease. Could be any kind of situation that we're interested in. Well, what's the prevalence rate? This is the probability that a subject is affected by this condition. So that we're going to find someone who actually has this condition or is in this condition. A very related concept is that of incidence rate of a condition. Again, people talk about simply incidence or incidence rate of a condition. Well, this is very similar to a prevalence rate, except that we're looking at the probability that a subject becomes affected by some condition during a specified period of time. Usually the most common period of time that people use is a year. So in the incidence rate, or incidence in general, we're looking at what is the probability that a person will develop a certain condition during a specified year. So may become sick or may acquire a certain disease or something like that. Related to both of these is the concept of mortality rate. This is a little bit more specific in that it is really the incidence rate, which means per year usually, but more generally during a period of time, and it's the incidence rate of death for a specified cause. So we're going to talk about the mortality rate for some kind of cancers. So that means, again, what is the probability that people will die of cancer during a certain year. All of these probabilities, being probabilities, are actually numbers between 0 and 1. But as numbers, they can be interpreted in one of two ways, and they are interpreted in one of two ways. So these numbers are interpreted as rates when they're referring to past observations. So if we're dealing with some kind of a descriptive study where someone has actually collected information about a certain condition and is telling us what the prevalence of this condition has been, then we talk about prevalence rate, and same thing for incidence and mortality. On the other hand, we can think of these as actual probabilities when we refer to future occurrences. So we say that the prevalence rate of cancer in the future will be this and that. So even though we're using the same word rates, but sometimes these rates are refer really to what they should be, namely to past events. Sometimes they are also interpreted as probabilities. And in fact, the one about probabilities is the more interesting one if you think about it, because in fact what we cannot do anything about the past. What has happened, but we do have a hand in what kind of things are happening in the future, even if it's just to get ready for it. And therefore, this interpretation of these rates as probabilities of future events is the one which is most interesting. There are some probabilities which are actually related not to epidemiology, or not so strictly to epidemiology, but to tests. And here by test I mean lab tests. Whenever a patient is suspected of having certain condition, it is customary to prescribe some tests to confirm whether in fact that patient has the condition or not, or even just to discover it. However, lab tests, even though our technology has gone a long way, are still not perfect. So sometimes errors can be made, and sometimes error can be related either to the fact that the test itself is not totally accurate, or to the fact that there may be some mistake in the performance of the test. So there are some probabilities related to this phenomenon. For instance, the sensitivity of a test is the probability of obtaining a positive result from a positive patient. So if a patient actually has a condition, whatever the condition is, and we run a test on this patient, will in fact the test tell us that the patient is positive? Will the test reveal that the patient actually has a problem? So this probability is called the sensitivity of a test. It tells us how sensitive the test is to the presence of a condition. On the other hand, we have the specificity of a test. And what is that? Well, that is the probability of obtaining a negative result from a negative patient. So in other words, if the patient does not have the certain condition, but we suspect that the patient might have that condition, and we run that test on the patient, will the test correctly identify the patient as not having the condition? So again, this is quite important. It's called the specificity of the test because it tells us how specific the test is to that condition, as opposed to being influenced by other conditions as well. Maybe a test is going to be triggered, is going to trigger a positive result not only by the condition that we're testing for, but also by other things. So in order to avoid that, we're looking at the probability of getting a negative result from a negative patient, and that's called the specificity. Now, notice that both of these values are actually values that give information about the test. It tells us how good the test is, right? So out of many patients who are positive, how many will the test be able to pick up correctly? Both in the positive actually and the negative directions. Okay. But as a nurse, you're probably going to be interested more in finding probabilities that have to do with the patient, not with the test. Maybe a lab technician will be more interested in these kind of numbers, and as a nurse you want to know something about these numbers as well. But more importantly, you want to know something about the probabilities associated with the patient, and we're going to see that in a minute. Before I go there, though, I want to point out the fact that there is another meaning to the word sensitivity when it comes to a test. So for some tests, the sensitivity is actually the minimum amount of a substance that can be detected by the test. So in other words, if you're doing, for instance, a blood sugar test, then this refers to the minimum amount of blood sugar that the test can actually detect. Or if you're looking for the presence of some unwanted chemical substance in the body, say alcohol, then the sensitivity of the test is the minimum amount of that substance that the test will pick up. Now, this is not a statistical concept, because it's a slightly different concept. Actually, not slightly; it's quite a bit different, different concept. So, whenever you see the word sensitivity being used, see, I get confused as well between sensitivity and specificity. So, be careful. Okay, don't feel bad if you get confused once or twice, but be careful and think about it carefully. Anyway, the idea is whenever you see the word sensitivity being used, make sure that you understand whether they're talking about statistical sensitivity or they're talking about technical sensitivity. All right, so now let's look again at the probabilities related to the test, but from a patient's point of view. Okay, so we're not so much interested in how well the test is doing. We want to know, okay, if a patient actually has tested positive, should we worry? And if a patient has tested negative, can we celebrate? Well, the two probabilities that are associated with this are called the predictive values. So the positive predictive value is the probability that a patient who has tested positive is in fact positive. So this tells us, well, assuming that we've done the test and that you have tested positive, what is the probability that you do in fact have the condition, and therefore should we be worried about your situation? On the other hand, the negative predictive value, you'll not be surprised to know that it's the probability that a patient who has tested negative is in fact negative. So assuming that the test has come back and it is negative, can we relax? Can we go home and celebrate? Can we forget about the whole thing? Or is there still a probability that this test was wrong and in fact the patient still has the condition even though tested negative? Okay. So these two again are the two that the patient may be more interested in knowing. Well, nurse, I've got this test which is positive. Should I write my will? Or nurse, I've got this test that is negative. Can I continue my life exactly the same way that it was before? And you'll have to understand how to interpret these two numbers. So let's have a look at a general sort of a hypothetical example to see how these all these values, sensitivity, specificity, positive predictive value, negative predictive value work. Okay, so let's say that we have collected data about a certain test, which is for a certain disease, and these are the numbers that we got. So we have tested 400 patients. Of them, 380 were healthy, and we knew that through some other means. We don't know how, but we knew that through some other means. And 20 had the disease. And of those 20, 19 tested positive, 1 tested negative. Of the 380, 30 tested positive, 350 tested negative. Okay, so let's say this is the situation that data collection gave us. Now, let's say we want to compute the specificity of this test. Now, remember, the specificity is the probability given that the patient has the disease. So what we have to do is we have to look only at the patients who have the disease. Remember, this is a probability about the test, not about the patient. So we're assuming the patient has the disease, and we're asking, well, what's the probability that the test will pick it up? So that means that we're focusing on that row of that contingency table. And we're looking in particular at how many of the people who had the disease will actually have tested positive. And we can see from the table that we had 20 people with the disease, and of them 19 tested positive. So that means that the sensitivity is 19 out of 20. The test picked up 19 out of the 20 people who had the disease, and you can write that as a percentage as 95%. Now, what about the specificity? Now, the specificity, remember, is computed under the assumption that the patient is actually healthy. And we are asking, well, assuming that the patient is healthy, what's the probability? So that we're looking at that row there. What's the probability that the test will correctly identify that person as negative? So what is the ratio between the number of people who were healthy and tested negative among all the people who were healthy? And again, if we look at the table, we'll notice that we had 380 healthy subjects, and of them 350 were classified as healthy by the test. So that means that the specificity is going to be 350 by 380, and if you look it up as a percentage, is 92.1. Notice that both of these numbers look pretty high. Okay, so you would think this is a good test and therefore it's reliable, and therefore you could tell the patient, well, if you got your test back, both the sensitivity and the specificity are around 95%. So that's how confident you can be that your results were accurate, right? Wrong. Remember, this is something about the test, not about the patient. So if we're going to look at the patient, we have to look at it from the point of view of predictive values for both positive and negative. So let's start at the positive predictive value, or PPV. Remember, this is done. Now, this is a probability computer under the assumption that your patient tested positive. And what we're going to be asking is, well, what's the probability out of that column now, because that's the column that contains the positive test results, what is the probability that our patient will in fact be positive? Not only have tested positive, but be positive. Well, if you look at that, then we notice that we have 49 patients who actually tested positive and 19 of them actually had the disease. So if you compute the probability, or if you divide 19 by 49, it turns out that if your patient is positive, that only means that the patient has a 38.7% probability of actually being ill, of having the disease. So we're far away from the 95% that we looked at from sensitivity and specificity. So this tells you something quite important, namely that the sensitivity and specificity numbers do not really give you a lot of information, or do not give you any information, in fact, when it comes to telling a patient how to interpret the results of their test. Let's look at the other one, the negative predictive value. So in this situation, we're looking at, well, what if the patient tested negative? Does that mean that the patient is healthy? So we're looking at that column, the column of the people who tested negative. And what we're asking is, well, what's the probability that the patient is negative and tested negative, assuming that the patient tested negative? So we're looking at those two numbers now, and we're looking at the ratio of 350 to 351. If you put that in your calculator, you end up with 99.7%. So a test which has these characteristics would be a test that is reasonably good, 95-92% specificity and sensitivity. It's not very high actually for modern standards, but I mean I use those numbers so that would make a little bit more sense. But on the other hand, you have to realize that with this test, if the patient tests positive, that's not the end of the story. The patient needs to actually be tested further, because the patient may not have the disease at all. On the other hand, if the patient tested negative, then there is a very high probability, of course with the usual proviso what very high means, but a fairly high probability that the patient is okay, and then the patient can be sent home and celebrate if you want. So again, remember these two sets of numbers, specificity and sensitivity on one end, and positive and negative predictive value on the other. They provide different information, and they need to be interpreted differently, and by all means don't use one set of probabilities when in fact you should be using the other. Let's look at another aspect of probabilities, of clinical applications of probabilities that is also quite commonly used, and that's the idea of relative probabilities. There are two major kinds of relative probabilities, and often they are confused, with each other. So we need to clarify what they are. The first one is something called the relative risk of an event. What do we mean by the relative risk? Here we're looking at the same event, but we're looking at it under two different conditions. So the relative risk of an event is the ratio of the probabilities of the same event under two different conditions. For instance, we might ask, what's the probability of developing lung cancer if you're a man, as opposed to what's the probability of having lung cancer if you're a woman? So we're looking at the same event, developing lung cancer, but under two different conditions. One is that you're a man, one is that you're a woman. So it's just a ratio, just a fraction, and I know that not many people like fractions. I don't like them either, to tell you the truth. But as long as we have a calculator to help us, then it's fine. So this is the relative risk. Very easy interpretation, and very clear and so on. However, the only thing that you need to be careful about is when we're talking about the relative risk, if we have a high number, it means that the risks associated to the condition that we're written in the top of the fraction is bigger than the one associated to condition written in the bottom, which means that whenever we are looking at the relative risk, we have to be very clear on which order we computed it. So which condition went on the top of the fraction, which condition went on the bottom of the fraction. So make sure that that you pay particular attention to that. Now, relative risks are again very easy to interpret. It's just if the relative risk is 3, it just means that there is the probability is 3 times as high to get to have that something will happen under the top situation rather under the bottom situation. But it's not always the one that is reported. Quite often, what people report are something called odds ratio. They are similar to relative risk. But they use a more complicated formula. Let me show you. So the relative risk, as we said, I'm using a little bit of a more mathematical notation here. So the relative risk is the ratio, fraction, of the probability that the event happens, given that, that's what that vertical bar means, given that, that's how it's read in mathematics. So the probability that the event happens, given that we are under condition A, divided by the probability that that same event happens, given that we are under condition B. Well, the odds ratio is given by this formula, and you can tell that it's more messy, right? So I'm going to go through one aspect of that formula in a minute, okay? But right now I just want you to look at that formula and say, oh my goodness, isn't that great that we're not going to have to learn it or use it, okay? Now you might wonder why, since relative risks has an easier formula and it's also easy to interpret, why do people bother with this odds ratio? It turns out that they're better suited for certain statistical methods that we're going to see in the winter. Okay, so for certain situations, mathematically speaking, you can do more things more easily with odds ratios than you can do with relative risks. And that is why people use odds ratio instead of relative risks. Now, you might wonder how come a more complicated formula allows you to do more things than a simpler formula. Well, you'll have to trust me on that one, or wait until you take your graduate level course in statistics. Now, one more thing that we need to know about these odds ratios is that they're connected to something called simply the odds of an event. And this is something that probably you have also heard before, but that we need to clarify and point out a couple of details about it. Okay, so if you look at that big fraction there, the top and the bottom, the fraction on top, the fraction on the bottom, are called the odds of their particular event. Okay. So, for instance, this one is going to be, we're going to call this the odds of the event E. And when we talk about the odds of the event E, we're not really focusing on the conditions. We're not really, again, it's not a relative risk anymore or a relative probability anymore. It's just a formula based on a single event. So in fact, what we're going to do is we're going to forget about the condition that it was attached to it. And we're going to say that the odds of an event is simply the probability of the event divided by 1 minus the probability of the event. But if you think about it, if an event has a 30% probability of happening, what does 1 minus 30% tell us? Well, it tells us that it's 70% of the probability of the event not happening. So we can think of the odds of an event as being the probability that the event happens divided by the probability that the event does not happen. Okay? Now, if you have heard the word odds of an event, probably you have heard it in connection with gambling. People talk about gambling on the odds of a horse winning a race or a football team beating another one, and so on. And this is really where this idea of odds should stay. But you're going to see them in healthcare as well. So again, you want to be a little bit familiar with this idea. Okay? Watch out for the interpretation though. Okay, there are two problems associated with this idea of odds. So again, I'm going to bring them up right now, but mostly with the idea of warning you, not necessarily with the idea of expecting you to go very deep in this area and try to compute all these things and so on, but just making sure that you understand that there are problems with it. The first problem is that if I say that the odds for an event are 4 to 1, okay, what does that mean in terms of probability? It doesn't mean that the probability is 1/4. Okay. In fact, remember, 4 to 1 remains, it's the ratio of the probability that the event is true to the probability that it is false, which means that altogether we have 5 possibilities, right? 4 that it is true and 1 that it is false. So the probability that the event will happen is going to be 4, which is how many times, what chances we have that it will happen, divided by 5, which is the total. Okay. And so that gives us 80%, not 75% or even 25%, as you might have thought about. So this is one problem. Again, if you're a little bit unclear about this computation, you may want to rewind and listen to it again, or simply remember that what I'm trying to tell you, that these odds can be very treacherous when it comes to interpreting. It's sort of like the standard deviation, right? Everybody uses them, but people sometimes don't know how to and end up making wrong conclusions about them. The other problem is because these odds were developed in the context of gambling, and because of the culture associated with that, they're often reported not so much as the odds of an event, but the odds against an event. So they're going to give us, when we're talking about the odds, we're talking about the probability of the event not happening quite often. And just as often, it may not be clear. Again, if you're dealing with a gambling situation, it's pretty much always odds against. But if you're talking about the healthcare situation, well, that could be odds against or odds for, and it's not really clear. So once again, you want to be aware of these problems. Try to stay away from odds ratio when it comes to interpreting them. Stick with relative risks, which are a lot easier. And hopefully this is an idea that will stay with you for a long time. The idea that in statistics there are certain things that are fairly commonly used but are not easily interpretable, and others which in fact are less commonly used but would be a much better idea to use. So that's it for this term. Hopefully you have learned lots more than you expected, and I certainly hope that I've been of help. And so we'll see you in the winter, and hopefully we'll have better videos and better classes, and we'll move on to inferential statistics, which is the much more interesting part of statistical practice.